Good afternoon. My name's Mark Jackson. I'm a professor in the School of Civil, Environmental and Mining Engineering, and I'm the current head of school. And today I'm going to talk to you about careers in civil, environmental and mining engineering. And I'm going to focus on how we learn from failure. So in my presentation, I'm going to talk about the 4 different programs that my school offers: civil and structural engineering, civil and environmental engineering, mining engineering and architectural engineering. And we're also going to explore 2 classic failures. We're going to look at quicksand and the Nagata earthquake, and we're also going to explore the Tacoma Narrows Bridge collapse and see what we can learn from those 2 classic failures. So let me start by talking about our programs that we offer in our school. So as I've just mentioned, we offer the Bachelor of Engineering Architectural, Bachelor of Engineering Civil and Environmental, Civil and Structural and Mining. And those 4 degree programs are, like all standard engineering programs in Australia, a 4-year degree. There are also a mixture of double and combined degrees. I won't go into those today, but more information is available in our program information leaflet, which is available at our display in the atrium, which is next to the Ingani Wardley building. And if you don't know where that is, I'm more than happy to show you where it is later on, because I'll be returning to there after this presentation. We also have a suite of postgraduate degree programs, masters and PhDs. And again, I won't go through those today because we're focusing our attention more on the undergraduate degree programs. For those that don't really know much about civil engineering, I'm just going to talk about some of the things that we get involved in. So it's made up of 5 disciplines. The first of those is structural engineering, which most people would be aware of. And structural engineers get involved in the design and construction of buildings and of bridges, towers, dams, and the like. Beg your pardon. I've jumped to water engineering, which is also about, crosses over between structures and water. So the second discipline is water engineering. So water engineering is also about dams. It's about water and wastewater treatment. So the water that we drink every day and take for granted comes often from the River Murray, and it goes through a filtration system at a number of locations around the Adelaide metropolitan area and gets purified, and chlorine gets added and fluoride. And civil engineers are involved in those aspects, as well as wastewater, the stuff that we put down the sink and the drain and the shower and the toilet ends up at a wastewater facility, and the facilities associated with those, the equipment and the processes are also things that civil engineers get involved in. We get involved also in open channel, such as you can see on the left-hand side of this screen, as well as pipelines and pumps and all of the infrastructure that is involved in those different aspects. I'm a geotechnical engineer, so I deal with the ground, soils and rocks, and we understand how soils and rocks behave when load is imposed upon them. We want to make sure that things don't settle too much, or that the ground is strong enough to withstand the load that we impose upon the ground. So the sorts of things that a geotechnical engineer gets involved in are pretty well summarised on this slide. So foundations, tunnels, retaining walls and things like that. It's also about landslides, and it's about settlement, and a classic example of differential settlement, that is the settlement from one part of the structure to the other, is associated with the Leaning Tower of Pisa. The 4th discipline that civil engineers get involved in is environmental engineering, and here you can see a breakdown of a number of things that are associated with environmental engineers: water quality, air pollution, wetlands, landfills, river health, and contamination of the ground and the groundwater system. And the last one is transportation engineering. It's about transport networks, such as the Northeastern Busway. It's about roadways and highways, and it's also at the micro level. It's about intersections and traffic flow. So all of those 5 different disciplines are what influences civil engineers. Just before I go into the differences between the different programs, I'll just focus my attention on some of the other aspects of some of our other degrees. So architectural engineering, for example, focuses on building design, and it involves studies from architecture. It incorporates structural engineering, geotechnical engineering, building services, sustainable design, and water environmental, but to a very small extent compared to the civil and structural degrees. So when we combine these together into a matrix, we'll look at these three degree programs which have some overlap. So you can see that in the first column here, civil and structural students would get involved in structural engineering, water engineering, geotechnical, but to a lesser extent in environmental engineering and transportation engineering. Civil and environmentals, for example, would focus their attention more on civil and environmental engineering and to a lesser extent to structural engineering. Architectural engineers, on the other hand, focus their attention on structural engineering, geotechnical, and to a lesser extent, water and environmental. Mining engineering, as I'm sure you're aware, involves extraction and processing of ore. It's about the design of mines. It's understanding the geology of the earth and about the strength and characteristics of rock. It's about ensuring that these operations are performed in an environmentally sensitive and safe manner. It's about estimating the resources that are in the ground and therefore involves mining economics and finance. You may or may not be aware that the University of Adelaide is a member of a consortium called Mining Education Australia. We're one of 4 universities, and the other universities are shown on the screen. So this consortium offers a common mining engineering curriculum Australia-wide. It's a fabulous organisation to belong to. There's a great deal of expertise amongst the 4 universities, and we share our resources and we share our expertise, and you can see the number of academics that are involved in the degree program. We get together every 6 months to compare notes, to compare the quality of our courses, and to ensure that our teaching is at the highest standard. It's actually not only a national, but it's also an international leader in mining engineering education. Our graduates are working in mines all over the country, and you might think that resources is going through a downturn at the moment, and that is as a result of, or has been as a result of, the high Australian dollar and reduced demand worldwide. But the demand for resources will continue to increase into the future as more and more of the things that we need and build require resources from the earth. And our mining engineering students attract the highest salaries in our school. So that's the background of the various engineering degree programs that we offer in my school. If you have more specific questions, I encourage you to talk to me or to my colleagues after this presentation. So for the rest of today, I'm going to talk about how we learn from failure. It's an innately human characteristic. To walk, we as children or babies, we would stand up and we would fall down, and we'd learn from that experience. We'd learn that falling down is painful, and we'd eventually learn how to walk. It's an essential characteristic of engineering too, that it's unfortunate that things fail, but we learn from those failures. And it's essential that we do turn those failures into a learning opportunity. As mentioned, I'm going to talk about 2 failures: the Niigata earthquake that occurred in 1964 and the Tacoma Narrows Bridge in 1940. So you might wonder what's the Niigata earthquake about. It's a classic quicksand or liquefaction failure. If you're as old as me and you've seen some movies where people drown in quicksand, then we've become accustomed to believing that people drown in quicksand, often shown by Tarzan movies. This is an old one, so most of us weren't born when these were around. Oh dear. No, you'd know that Tarzan's a good guy, and he didn't go to the rescue of those two gentlemen, and that's because they're bad guys. They just plundered a temple of gold and antiquities, and you saw him picking those up a moment ago. So we've been brought up to believe that quicksand, that people drown in quicksand. Does anybody know who this gentleman is? The Hood. Good man. From? Thunderbirds, that's it. So the Hood from the Thunderbirds. Reason I mention the Thunderbirds or the Hood is because I have a scale model of the Hood, and I'm going to put him into quicksand. And I'm going to ask yourself, I won't ask you to put your hands up, but I'll ask you to think about whether this model would sink or float in quicksand. And you might say to yourself, well, of course he's going to float because he's made of plastic. Well, this slide is a slide which shows some statistics from a couple of doctors that performed some research in 1978 on 308 men. And this shows the specific gravity of a human person. So I've weighed this individual and I've measured his volume, and his specific gravity is about 1. And that's our specific gravity essentially. We weigh about this. We weigh about, well, not weigh, but as I said, our specific gravity is equal to 1, which means that our weight or our density is similar to the density of water. And here you can see that our specific gravity or body density is about 1. Don't worry about the x-axis because that's exploring how we might measure the density of a human being based on the skin folds. However, this person or this model has a specific gravity of 1, and I'm going to lower him into quicksand now. So quicksand occurs in nature when we have water flowing vertically upwards through a column of sand. So what I have under here is a pump and a reservoir of water, and what I might do is just go to the camera. Those that can't see at the back. So this is what we call boiling sand or liquefaction. Its correct name is. So I'm just going to lower him in and we'll see what happens. So you can see as much as I try, he's not actually sinking in quicksand. Let me show you another example of that came from the Mythbusters episode a little while ago. And the myth that they were exploring was, do people sink in quicksand? Oh, I'm not sure what's happened to the sound in that one. Apologies for that. Ah, camera off. Good. Oh, you can't see. Thank you. That's why it's not working. Thank you. I'll rewind it. Sorry about that. That's better. Okay, so you saw that it's not just my equipment or the model that is showing that, but it actually occurs in real life. So where does that occur actually in real life? It's when, as I mentioned, it's when we have water flowing vertically upwards through the ground. Unfortunately, that doesn't happen terribly often. So it might happen as a result of water that is draining underneath a dam. So in this location here, which might lead to actually a piping failure of the dam, which is quite dangerous. It might occur at the beach when we've got water flowing from a hillside and flowing towards the sea. The sea is salty and therefore is more dense, and fresh water is actually less dense and so can sit on top of the salty water, and we can get water percolating from the ground as a result of that. So what's the story with Tarzan? Why did we see those gentlemen falling in the quicksand? Well, it's actually a bit of a trick, and I'm going to show you what's going on here. You can actually see it's not sand, it's actually mud, and you'll see the fellow's knee coming up there. He's actually lying down as they go there, so it's just a trick of photography. So what I'm going to show you is a situation that occurred in Niigata in 1964. This is a model of a building complete with a flag on top that the guy's made for me. Actually weighs 5 kilograms. It's solid bronze. It's quite heavy, and it's not going to sit down because still some. Let me just see what's. Need to drain the water down a little bit more. So I just need to put that down. So what I'm trying to do here is, you can't see again. What I'm trying to do here is simulate the same kinds of ground conditions that occurred in Niigata in 1964, where the water table was close to the ground surface. So when I place the building on the ground, you can see that it sits there happily, but along comes an earthquake, and watch what happens. So I wonder what happened there. What happened with the earth, with the building, why it fell down. Normally in a class I would ask for questions a bit more difficult here. What happens? An earthquake is a wave that propagates through the ground. Because the sand is essentially beneath the water, the motion causes the particles to vibrate relative to one another, and so the particles separate for an instant in time. So for a moment, this building felt like it was on water, and hence that's why it failed. I just remembered that I've forgotten to tell you why people float in quicksand rather than sink. And that is because the combined density of the sand and the water is actually more dense than water by itself. So it makes sense that we actually float in quicksand. The other thing to bear in mind is that the buoyancy is greater because I had a flow of water upwards through the ground, and that adds to the person's ability to float. Okay, so the question is, if we were... just let me go back a little, and I need to go to that. So this is what occurred in 1964. You can see a whole bunch of apartment buildings that have fallen down in a very similar manner that I've just shown you just now. It's not terribly often that we get to see the underside of a building. So the question we ask our students is, if we were confronted with a site like this, what would we do? Would we walk away from it? How could we design a structure to withstand these kinds of situations? So what we could do is we could put some piles into the ground. So you can see here that the piles would go through the liquefiable material, the sand, and then sit on a firmer stratum, which in this case would be gravel. Another option that you may not be aware of is a thing called vibrocompaction, which is where the density of the ground is increased, and that's by basically placing a giant vibrating mechanism into the ground. So what I'm going to do is simulate that. So essentially it works by doing this kind of thing, by allowing the ground to settle more, and its density and therefore its strength increases. So you can see that the ground settled more, little bit more. So I'll keep doing that a bit. Just wait for it to settle down a little bit. Now you can see it's a lot stronger. Can actually get it to fail eventually, but you can see it needs a fast, greater magnitude earthquake for it to fail. And this is a photo or a video taken by one of our PhD students after the Christchurch earthquake that occurred in 2011. And you can see the water bubbling up through the ground several hours after the earthquake. Many houses had to be abandoned in Christchurch as a result of this. Okay, now I want to move on to another collapse, which is the Tacoma Narrows Bridge collapse.
In 1940, barely 3 years after the Golden Gate opened, the Tacoma Narrows Bridge was completed in Washington State. Designed by Golden Gate consulting engineer Leon Moisieff, it was the culmination of his career-long effort to make suspension bridges slim, elegant, and economical. But this bridge moved up and down like no other before it. Then, just 3 months after it opened, in a steady 40-mile-an-hour wind, the Tacoma Narrows Bridge began to twist as well as move up and down. In 4 hours, the bridge tore itself apart. Years after the collapse, investigators using test models and wind tunnels finally figured out what caused the disaster.
Well, the Tacoma Narrows was a different type of bridge than had been built before. Instead of having a truss hanging underneath the cable, it had a girder, which is a solid wall-like structure that obstructed the wind. And if a little piece of wind makes the bridge twist ever so slightly, it has a profound effect upon the wind that's coming around it. It forces the wind to behave like a major climate change right on the bridge.
The moving bridge began to fan the steady wind into a swirling motion, which created many high and low pressure systems called vortices. These in turn forced the bridge to increase the motion it already started.
But it's like somebody on a swing. A little push now, a little push later, at exactly the right time, builds up into tremendous amounts. It's called properly a self-excited vibration. The bridge took the wind over and made it cause the bridge to fail.
Even with its design flaws, a heavier bridge might have resisted the wind pressure. But Tacoma was built light to save money and suffered the consequences. Other Moisieff-influenced bridges, even those with stiffening trusses like the Golden Gate, were immediately reinforced with bracing systems that restrain twisting motions in the wind. So far, these measures have prevented another Tacoma, but the problem of excessive movement has not been entirely eliminated, as this 1982 footage of the Golden Gate clearly demonstrates. In high, steady winds, the bridge can move radically up and down, placing tall trucks in danger of blowing over. The bridge is now closed for high winds. But in engineering, most things are trade-offs.
So that was the Tacoma Narrows Bridge. Just like to, as I wrap up, just to focus on a few possibilities for civil, architectural and mining engineering So if you choose a career in one of those disciplines, you might be involved in perhaps designing and constructing the tallest bridge in the world, such as the Mayu Viaduct in France, or the Ikashi Kaiyekyo Bridge in Japan, which is the longest suspension bridge in the world. They're thinking of, and currently there's plans underway to design and build the longest, will be, if it ever gets off the ground, be the longest suspension bridge in the world, which will span the Sicily to mainland Italy across the Strait of Messina. You may be involved in the design and construction of the tallest buildings in the world, as the Burj Khalifa in Dubai or the Taipei 101, or the largest dam in the world, Three Gorges Dam in China. You might think, what's that got to do with Australia? Well, up until recently, we had the tallest residential building in the world, Q1, on Gold Coast, which is an 80-storey high building, 323 metres high. Checked on Google, on Wikipedia the other day, and it's down to the 5th now. However, our engineers, I'm aware of some geotechnical engineers from Australia that actually designed the foundations for the tallest building in the world, the Burj Khalifa in Dubai. Or the 12th tallest now, a residential building, which is the Eureka Tower in Melbourne, which is 91 stories high. Closer to home, I went to a talk the other day where we were informed that the roof for the new Adelaide Oval is going to be the longest span dome in Australia at 168 metres. When the Olympic Dam project goes ahead, it'll be the largest open-cut mine in the world. So why choose to study at the University of Adelaide? It's the third oldest university in Australia. It's internationally recognised for excellence. As from next year, every first-year student and second-year and third-year and fourth-year student will have a small group discovery experience with senior academics. There'll be increased study abroad opportunities and scholarships for disabled students. Why choose to study in my school? Well, we are among the top civil and mining engineering school in Australia. We have award-winning teachers, and our research is regarded internationally. Our qualifications are regarded internationally. We have students working all over the world, and our students are in high demand both locally, nationally and internationally. Why choose a career in engineering? There's 10 reasons there on the screen. Love your work and live your life too. Be creative. Work with great people. Solve problems. Design things that matter. Never be bored. Make a big salary. Enjoy job flexibility. Travel. Make a difference. Change the world. So the careers that my school offers are those that are listed on the left-hand side. Where might you work? You might work in private practice or in government, as a consultant, in the construction industry, in mining. But our degree, because it's problem solving and has unique skills, people skills as well as engineers are numerate, they understand numbers, they understand how to solve problems, then our graduates are increasingly working in the finance, banking, insurance and legal industries. If you're interested and you have more questions, there'll be, as I said before, there'll be opportunities for you to ask those questions of us from the Ngani Wardley building in the atrium, which is just situated around the corner from here. More information is also available on our website. There, as I say, there's some exhibition displays areas. Also, our student centre is available for answering questions, and there'll be an open night on Wednesday the 11th of December where you can get a feeling for what it's like to live, and not live, but be a part of the community at the University of Adelaide. Thanks for your attention. I hope you enjoyed the presentation. Thank you.